What's up, everybody? Okay, so let's do this. We're looking right now at a 2011 AP Physics C mechanics problem, specifically question number 2. And this problem is looking at some energy conservation and some forces as well. So what we've got set up here is a cool amusement park ride. It used to be called a demon drop, but essentially you fall down this incline here, and then it slits you like onto your back, and you sit like that. So you fall down this compartment. It has a mass m here, and it's released from point A, and it will move all the way along the track, all the way out to here. It's falling in free fall between points A and B, but as soon as it hits point B, it starts going around this curve right here. And as it hits this curve, it's a perfectly circular curve, but there's still no friction. And then it moves down the curve to point D, and then it just slides horizontally flat out to E. So what we are asked to do is, for part A, little free body diagram action, on the dot below that represents the passenger compartment, we're drawing and labeling the forces, not the components, that are acting on the passenger compartment when it's at point C right here. And this point C is going to come up a few times. So, which is at some angle theta from point B. So the two forces that we have here, and there are only two forces that we have here, is we always know that acting inward towards the center of the earth or down on an object is its weight, or the force of gravity. So we can just say here, this is weight, which equals mg. We have one other force here, and if you think about going through a bend like this, as you go into the bend, it kind of feels like something is pushing down on you, and if you've ever been in a car and just made a big turn like that, it feels like you get thrown to a slide. But that pushing back on the object or on you, that pushing back through the turn here, that is your normal force. That is the force from the surface pushing back on the object. So that normal force is going to come out perpendicular to that line right there, and there's our normal. Okay. Now, if you're on a flat surface, the normal is equal to the weight, but since we are on some sort of incline here, we're at some angle, that normal just has some value. We'd have to figure that out later. Okay. What we're asked to do in part B, in terms of theta and the magnitude of the forces in part A, the normal and the weight, we're determining an expression for the magnitude of the centripetal, that inward acting force, on the compartment at point C. If you need to draw anything besides what you've shown in part A just to assist, use the space below. So once you've written out your part A solution up here, leave it alone. Okay, we're going to break some stuff up and draw some more pictures because this part B can be a little bit weird if you don't have an idea of what you want to draw. But for right now, let's not draw anything up above. That's our answer. Okay, so in part B, I guess I should say B right here. B. Let's just draw this first. This is going to be our... This is kind of a weird thing to draw. Let's have that be the curve, and this be point C right here. If we draw a line tangent to point C, that line will look like this. And if we set a point at the center of our curve here, this we have as some angle theta. Now, I know that this inward acting force is going to be some amount as given by the normal, but this weight is also broken up in 2 dimensions. Some of this weight is acting along the curve or on the plane, and then some of it is acting kind of into the curve. And because of this, I'm not just going to be able to say that my centripetal force is equal to the normal. I'm going to have a little bit less force there as well. So what I'm going to do, and this is kind of weird, is I'm going to backtrack this pink line like this. And the reason why I'm doing that is on the other side here, I'm going to flatten out this bottom. And the reason why I'm doing this is normally whenever you have an inclined plane like this, we use the angle theta here. And we would say something along the lines of like, hey, if this is our object, you know, this is mg sine of theta acting down the plane, and into the plane would be the mg cosine of theta term. Because we're given this angle down here. But in this case, that's not the angle we're given. We're given this angle up here, right here like that. And because we're given this angle, as kind of seen in this picture here, right there, I'm using a little bit of geometry here to actually figure out what would the real angle I'm looking for here actually be. And what I'd see by geometry is that this angle on this side right here is actually the same angle up top. So this is angle theta. This right here has to be 90 degrees on both edges, which means that the angle I have down here in the corner, this is like 90 minus theta down here, which is a little weird to think about, but that's what I have. I have 90 minus theta. So when I look at my forces acting at point C, what I have is I have this inward acting normal force. That's our normal. But then acting away from that, I have some component of the weight. And that component of the weight I have, while we would normally call it mg cosine theta, based on that angle, because we're 90 degrees shifted from it, we are actually going to call this here, this is going to be an mg sine of theta. Or if you wanted to, you could say it's mg of cosine 90 minus theta. Both of these are the same. You just need to pick one there. What this means is that when we're saying what are inward acting forces here, I'm going to call acting inward to be positive and acting outward of the circle to be negative. My centripetal force is given by the normal force minus mg, and I'm going to use sine because it's got less features to it, sine of theta. That is what we have as our centripetal force. Kind of weird to get that sine component there because we're normally used to saying cosine, but in this case, based off of the angle they gave us, we had to do a little bit of math to figure that out. Kind of an annoying thing, but it is what it is. For part C, we're asked to derive an expression for the velocity of the passenger compartment as it reaches point D in terms of m, r, and fundamental constants. Now this is actually something that everybody can do, whether you're in an AP physics class or just in an intro physics class, because there is no friction anywhere along this path. And since there's no friction from path A to path D, that means we can conserve energy. In class, this would be like the roller coaster lab or just dropping an object. And all we need to know is the starting height here and the ending height here. And that ending height, we would probably make our reference position of 0. From there, we just need to go up a radius r and then up an extra distance given by 3r over 4. So we can just say due to the conservation of energy that this value comes about very, very easily. We can say that mg delta h equals 1/2 mv squared, where this is the v at point D. And what's real nice about this is we immediately see that the mass of that cargo carrier, that cart, the passenger compartment, doesn't matter at all. You could put small children in there, you can put big adults in there, you could put an elephant in there, and on a frictionless surface, the mass of the cart does not matter as it's moving. All that matters are these other features. So what we'd quickly see by multiplying by 2 and then taking the square root is we see that VD equals the square root of 2g delta h. And since we want this in terms of r, we need to get that delta h, and remember that delta h is that full distance going up. It's the radius value plus that extra one. So we can say this here is the square root of 2g and then if we take a look at r plus 3/4 r, well, r is like saying 4r over 4. So this together can be thought of as 7r over 4. So we can plug that in down here into our answer. 7r over 4. Okay? And if we wanted to, we can actually just leave that answer like that. There's nothing wrong there. If you have a math teacher or something like that teaching this to you, they'd be like, clean that up, in which case you would whoosh, whoosh, do this, and you'd get the square root of g 7r over 2. But all of those are fine, okay? Anything over here is good. Okay, so that's just a conservation of energy, pretty straightforward there for us. You know, you probably saw that last year in an intro physics class, or you saw it again this year in your AP class. In part D, we are looking at a force now acting on the compartment during the flat region out here. There's a force that's slowing the cart down. And we are assuming that this is a frictional force, and we'd like the numerical value of the coefficient of friction mu. Okay, so how do we do this? Well, we know that if this cart is going on a horizontal surface here, so let's draw our surface, and it's slowing down, nothing is pushing it forward. The only thing acting on it is this force of friction, which we know is mu n. The coefficient of friction multiplied by the normal. So how can we kind of go about this and figure out what's going on here? We know that this cart has a velocity here. It has a velocity of vd, which we found from above. We know it's going to lose all that velocity and come to rest, which means that work needs to be done on this cart. So what we can say is we can say that work, which is given by a force dotted with a displacement. Remember that dot product is just giving a directional vector there. And in our case, this force is equal to the change in kinetic energy. This is known as the work energy theorem. It is a very big thing, not only in Physics 1 and Physics C mechanics, but also in Physics 2 and Physics C E and M. So what we can say here is the force acting on our compartment here is the force of friction, and this is how far it's going to go. That is the distance between points D and E, which is 3r. Okay, so we got some values here. We can do this. So what we can say is mu n times some value of gone, 3r, is equal to the change in kinetic energy. Now remember, a change here is always a final minus initial, so our final is actually going to be 0, and then 0 minus the initial value is minus 1/2 m, and then this is going to be vd from above. So let's write this as root g 7r over 2. Okay. Well, I can replace this normal force, because we're on a flat surface, with mg. So let's just rewrite this real quick. Mu mg. With that, we see our m's go away nice and quickly. What else can we say here? This negative is actually going to go away, because on this dot product here, this force is opposing the direction. The direction this object moving is to the right, but its force is to the left. So this is actually a negative here. That's because there's a cosine of theta term, and that theta is 180. So the negative and the negative quickly go away. And now we just have to solve for this ugly mess. Oh boy. Okay, well, let's do it. I like to put things in more parentheses when I solve them. So I'm going to say u times 3gr equals 1/2 times the 7g over 2r to the 1/2. If if I divide everything by 3gr, those wipe. And when I divide by 3gr, what we'll quickly find is that this half r will go away, and I'll get a half here. This g will go away, and I'll get a half here. And then this 3 will pop into the denominator and become a 6 down there. So I should get, oh boy, this is going to be annoying. 1/6 times 7 over 2gr to the 1/2, right? And then, did I mess something up somewhere? Oh, I know what I messed up. Son of a biscuit dough. I messed this up a while back. See, I know I'm messing this up because I've got this square right here, and I don't want this square right here. The reason being, we'll get rid of some of this. We don't need to get rid of all of it. The reason I don't want this root right there is because this is velocity squared for kinetic energy. It's 1/2 mv squared, and because it's v squared, I'm actually going to lose that radical, which makes life so much easier. When you lose the radical like that, the g's actually divide out and the r's divide out, which is so much nicer. And whenever we have this, we can say that this is mu equals 7 over 2 times 2 is 4, 4 by 3, because when I divide the 3 under, is 12, 7 over 12. And that's just it. That's it. It's unitless, so that works well. Mu is always a unitless quantity. Technically, it's newtons over newtons, but it's a unitless quantity. So yeah, oh boy, how did I forget that square? 1/2 mv squared makes that so much easier. It's kinetic energy, people. Kinetic energy is 1/2 mv squared. Don't mess it up like me. And yeah, if you do get part C wrong, like you messed up this velocity here, you will get consistency points down here. They're giving you a point in this problem for having that work is equal to change in kinetic energy. An equation for the frictional force right here, so that's a point, and then you get your third point for your final answer. So do your substitution. If for whatever reason your math starts going down a rabbit hole like mine was, just skip, move on to the next part. Normally if you're doing the math right, the math is very straightforward and easy. So, okay. But yeah, you can get a consistency point here if you're, and really there's not so much of a consistency, it's just more like, do you have the main concepts right? The third point is for you just getting the right number. Okay, up till now we haven't done any calculus, but now we're getting to the calc of it. And the calc we're going to do in part E is actually identical in many ways to the calculus from the 2008 AP Physics C problem number 1. And in this, we are asked to look at a braking force minus kV acting on the compartment instead of friction, where k is a constant and v is given by the velocity of the compartment here. So what they're asking us to do in the beginning is to write but do not solve the differential equation, which anytime you see that, especially in a problem like this, we're looking at forces, we are looking at F equals ma, and this all of a sudden becomes the only forces acting on our object minus kv equals m, and then our acceleration turns into a dv dt. That's it. That's that part right there. Okay. Anytime you see write but do not solve the differential equation, you are always writing the force that is being applied, or the net forces, and then dv dt every time. That's what you want. 2 points right there. Now we get the wonderful pleasure of solving this. And to do this, we need to run a separation of variables. I'm going to do this quickly. If you want to see a more in-depth version of it, go check out, like I said, the 2008 problem number 1. There's a video of it I have in the YouTube somewhere. But I'm going to move this velocity over with the dv. I'm going to move the m away because it's not a v, and I'm moving the dt away because it's not a v either. So what I'll get here is negative k over m dt equals dv over v. And now what I have to do is I have to integrate this. K and m are constants here, so I'm going to pull them just to the outside of this integral, which is just going to integrate the dt from an initial time of 0 to some time t later. And then the dv over v goes from some initial velocity, which is actually in our case vd. It's not 0. We are moving at some speed initially whenever this starts. And then we just want it at some, so they just want it at some time later? Yeah, so some velocity at some time later, okay? So that's just what we're setting up there. Looking at this and kind of working this around, the integral of dt is just t, and then bound from t to 0 just gives me a t. So I've got negative kt over m, and this is going to equal dv over v is a natural log here. So what we can say is that this is the natural log of the quantity, and then this is going to be v of t, and then minus the natural log of v of d from the upper minus the lower bounds. Maybe you remember your log rules. Whenever you are subtracting logs, you can divide them. So this is actually going to equal the natural log of v of t over v d. And then if we would like to get rid of our logarithm here, we can exponentiate both sides. So we exponentiate the right here, and that brings our exponential way over to the left. So what we have now is v of t over vd, that initial velocity, equals e to the minus kt over m. And then last but not least, we will just multiply each side by the vd to remove it. Wink. And that gives us our solution. Okay, so that was a pretty quick integral, actually much easier than the 2008 problem, but you got to know your integrals, you got to know your natural logs there. If you don't, skip it, because all of this integral we did here was officially worth 2 points. You got 1 point for the end piece, and you got 1 point for separating the values and integrating. So if you didn't know how to do that, like, who cares, skip. For the last part though, we're asked to sketch a graph of the magnitude and the acceleration of the compartment as a function of time. We're explicitly labeling any intercepts there. So what we do know is our acceleration is going to be greatest at the very, very beginning. If we actually take a look at this, well, how do I want to think about this? Because we're looking at a function of time. Yeah. Okay, so there's not really a great way to do this. Just thinking about it, we can't think about it falling at all because it's moving horizontally. But what we do know is that the derivative of the velocity is an acceleration. So if I take just the derivative of this up here, I know the derivative of an exponential is going to be the derivative of the exponent of it. So we're going to get out of there a, what would that be? We're going to get out of there a negative k over m times vd, and then e to the minus kt over m, because we're taking this derivative as a function of time. This acceleration, we're just looking for the magnitude of it. So even though there's a negative, I quite frankly don't care. It does not matter to me. That acceleration just means we're slowing down, but in terms of just the magnitude of it, this is the maximum piece that I will have. v dk over m. I know that's the maximum because if I set time equal to 0 initially, then e to the 0 is just 1, which means my acceleration will be equal just to this in the very beginning. As time goes on, this exponential is a negative. So we're going to have a curve that is actually like this, where this right here is our asymptote, t. And that's that. We just took a derivative in order to find that for the acceleration. In theory, we could have done that without taking this derivative as well. What we could have done if we wanted to, if you kind of have this kind of thinking, if you came back up here to the beginning and said, hey look, kv over m equals the acceleration initially, assuming that this velocity is d, then that is that max acceleration here. What it is later on, well, we have to use the function in order to get that, and we kind of see that from this exponential here. So however you like to think about this for the graph, you can do that. I just like taking the derivative if I can for something like this. Free fall, it's a little easier to think about, but that's all it is there. And we actually got 3 points for this last part. You actually got a point for taking the derivative here, which was kind of neat. I don't think you actually had to, but you got a point for it, you got a point for labeling that, and you got a point for making sure this is concave up with an aspect. So that's it. That's that problem. It's a 2001 APC problem, had a little bit of energy, or 2011 problem, excuse me. Had a little bit of energy in it, had a little bit of centripetal motion, a little bit of integration, just overall a great problem there. But with that, we have finished this. This is all done.